Start recording. Good. So now what we're interested in is sum of the first n terms. So I'm trying to compute the sum of the first n terms. So I start by the first term, which is a, followed by the second term, which is a plus d, followed by the all the way to the nth term, which is a plus n minus 1. Now, before I generalize this, let me give you a concrete example which will guide us on how to find a general formula for sum of terms like this. So let's say you have a sequence, numbers 1, 2, 3, 4, up to 10. This my sequence has the first term as 1, the common difference of 1. So 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, all the way up to 10. The first 10 positive integers. Okay, now I need to compute the sum of the first 10 terms. I want to compute 1 plus 2 plus 3 plus 4 all the way to 10. Now, a common trick that we usually use is we know that addition is commutative. So when you add 2 plus 3 is the same as adding 3 plus 2. So it's usually you rearrange these sums in the reverse order. So instead of starting with 1, I start with the one after n, which is 10. 10, and then after 10 there is 9, and there is 8, all the way up to the first term 1. So I've not done anything. I've just rearranged to start with the last term or the 10th term to the first term. Then now what I do, I just do the addition, okay, vertically. So S10 plus S10, this is just 2 S10, just like x plus x is 2x, y plus y is 2y. Then now I add for each and every column. So 1 plus 10 is just 11. 2 plus 9, well, that's still 11. 3 plus 8, still 11. All the way to the last term, 10 plus 1, you still get 11. Now, you notice that for each and every term you have, when you add them, you're getting 11. What you have here is that twice the sum of 10 terms is 11, and 11 appears how many times? 10 times, because you have 10 terms. So this one just compute 11 times 10, because you're adding 11 to itself 10 times. So we have twice S10 is 110, where 110 is 11 times 10. So 10 is the number of times this 11 is appearing. Now to find S10 that I was interested in, I just take 110 divided by 2, this will be 55. This should be the sum of the terms from 1 up to 10, and you can confirm calculator. So we want to generalize this idea for any arithmetic sequence for which there's a fixed common term, first term, and then there's a common difference. We want to generalize how do you find the sum of some given fixed number of sums. So just as we have done here, we're going to write the terms from the first term to the nth term which we're interested in, or the last term for that matter. Then because we know addition is commutative, we rearrange, we simply reorder this so that we start with the last to the first, and then add vertically like this, and then try to come up with a general formula for summing the first n terms. So what I'm going to do, I already have the terms from the first term to the nth term. Now I need the same sum, and I know it's going to be the same because addition is commutative. So start with the last term. So here we have a plus n minus 1 d. Okay. Then the second last term. The second last term will be a plus n minus 2 d. All the way to the first term. The first term will be just a itself. Now, like we did in the previous example, we're going to add these terms vertically. So Sn plus Sn is simply twice Sn. Then now take a plus a times n minus 1. So a and a gives you 2a plus n minus 1 times d, plus, how about a plus d and a plus n minus 2d? So a plus a, that's just 2a. How about d plus n minus 2d? So remember, n minus 2d simply nd minus 2d. To this, you're adding d. So this one plus d will be n minus d, because minus 2 plus 1 is minus 1. And then when you factor out d, you have d into n minus 1. So here again, we have n minus 1 times d. If you continue for all the terms up to the last one, this side, so a plus a is 2a plus n minus 1 d. Notice that for each and every term you're adding in this sequence, we get to the same term, 2a plus n minus 1d, 2a plus n minus 1d, 2a plus n minus 1d. So as we did before, there are n terms that we're adding here. So this simply means that twice Sn is n times this term, 2a plus n minus 1d. And now to compute Sn, just divide both sides by 2. And this is the formula that you need to remember. General, for any arithmetic sequence, Sn is given by half of n, 2a plus n minus 1d, where a is the first term, d is the common difference, n is the number of terms. Or alternatively, we know that we can write this as Sn is half of n. Instead of writing 2a, I can write it as a plus n minus 1 d. What is this term? A plus n minus 1 d. From the previous class, what is the term a plus n minus 1 d? Anyone remember? Anyone remembers what is the term a plus n minus 1 d?
Is it the first term?
The first term is a. This should be the nth term. Remember this expression? An is a plus n minus 1 times d, where a is the first term of the sequence, d is the common difference, n is the number of terms that we're dealing with. So this a plus n minus 1 is just the nth term, so that you can, another way of writing this formula is Sn is half of n plus a plus an, where n is the number of terms. So an will be the nth term. So this is the formula that you need to remember. This is what we use to compute the partial sums for an arithmetic series. Any question before I give an example? So I'll start with the example that we did, the sequence of 10 terms. So compute the sums of the following arithmetic series: 1 plus 2 plus 3. Compute, so this one you want to compute the sum of the first 10 terms. The formula tells you Sn is half of n plus twice the first term times n minus 1 times the common difference. So your goal is to identify what is a. So what will be a in this? A will be the first term, a is going to be 1. D is the common difference. So for each 2 consecutive terms, find the difference. That is the common difference. 2 minus 1 is 1, 3 minus 2 is 1. So D is 1. We are interested in 10 terms. That means n is 10. We have exhausted all the terms that we need in the formula for us to be able to find the sum of terms in this sequence. So now the sum of the first 10 terms will be, I'm just substituting for where there is n, I put 10. So that's going to be a half of 10 multiplied by twice 1, or 2 times a, plus n minus 1. So n is 10, so I put 10 minus 1 times 1. Well, this gives me half of 10 is simply 5. 2 times 1 is just 2. 10 minus 1 is 9. Now, this is very easy. So 2 plus 9 is 11. 11 times 5 gives you 5. And that is what we found by adding the first 10 terms in this, the first 10 integers. The common difference is 1, and the first term is also 1. Let me give you another example. I want to use the example that we did last time. So suppose you are told the fourth term of an arithmetic progression is 7, and the 10th term is 29. Find the sum of the first 400 terms. Fourth term is 7, 10th term is 29. Find the sum of the first 400 terms. So we have the formula. The formula is that the sum of terms should be half of n plus twice the first term times n minus 1 times the common difference. So with this information, we need to look for these inputs. We need a, the first term, the number of terms is given. So we need the first term and the common difference from this information. We know that the nth term, or simply, let me just put an, a plus n minus 1. So we are told the fourth term is 7. So that means a4 is a plus, so it's the fourth term. So 4 minus 1 is 3. So that is a plus 3d. And you're told the 10th term is 29. So that means a10, this guy is 7. A10 is a plus n minus 1. So when n is 10 minus 1, that's 9. So 9d, this gives you 29. So here you get two simultaneous equations, but you get linear equations in two unknowns, and it's very easy to solve. By elimination, just subtract this. So this is the first equation, second equation. If you subtract from equation 2, equation 1, we get that a minus a is 0, 9d minus 3d is 6d, 29 minus 7, that is 22. And then from here you can find d. So d is just 11 divided by 3, which is 22 divided by 6. Now once I have d, I can put it in any of these equations and find a. So using equation 1, from equation 1, a is supposed to be 7 minus 3d. So a is going to be 7 minus 3d, but d is 11 thirds. So what's that? This is going to be minus 4. So we have all the information we need. A is minus 4 and d is 11 thirds. We can go ahead and find the sum of the first 400 terms. So just substitute as 400 should be 400 divided by 2 times twice a. So 2 times negative 4 plus n minus 1. So 400 minus 1 is 399. Okay. And then the common difference is 11 thirds. So this guy times 11 thirds. At this stage, just plug this in your calculator and it will give you the sum of the first 400 terms. Very simple, because we did not have to compute, we did not have to know what are these 400 terms. I don't need to know which is the second term, which is the third term. I can just compute the sums by plugging this information of a and d in the formula. So this is how we find the sum of partial sum of terms of any arithmetic equation. Any question? This is the formula we need to remember. Is there any question? No question.
Wait.
Yes. You have a question?
No, sir, we haven't written that part yet.
You have not written this part yet. But don't worry, the class is being recorded. You'll find this. Huh?
Okay, sir.
Yeah, don't worry. The class is being recorded. You'll find this. I will upload it at the end of the class. There are so many applications of these arithmetic progressions that are applied in finance, studying population, all kinds of modeling. So let's look at geometric series. Geometric series. So we've been studying an arithmetic series where you start with a first term, and to this first term, to obtain other terms, you keep adding this fixed difference, or this what we're calling the common difference. Now, a geometric series is simply a series in which the ratio of any two consecutive terms is a constant. So a geometric series, this is a series in which the ratio of any two successive terms is constant. Okay, the ratio in which the series in which the ratio of any two terms is constant. So it's usually a series of the form S given by A plus AR plus AR squared all the way to AR n minus 1. You can go on. The first term. And R ratio. R is common ratio. What that means is that if you pick any consecutive term, hello?
Yes, after the S equals to A plus AR plus AR what? From there I can see.
AR squared. And then this is ellipses, 3 dots, and then it goes on to AR n minus 1 plus, and then these 3 dots, ellipses.
Okay.
Yes.
Thank you.
Okay. So you notice that if you find the ratio of any two terms here, for example, AR divided by A will give you R. AR squared divided by AR will give you R. So any two terms which follow each other, the ratio of them is always R. That's what we're calling the common ratio. Okay, so let's see an example of a geometric sequence, a sequence in which there's a constant ratio. An example, I'll give you a very simple example. This sequence that starts half, then a quarter, then you have an eighth. Generally, you have a half raised to the n. This is an example of a geometric sequence. So it's a sequence in which the ratio of any two successive terms is common. So for example, to compute R here, so of course we know A is a half because it's the first term in the sequence. To compute R, find the ratio of any two terms, any two successive terms. So R should be given by a quarter, or you could take an eighth divided by a quarter. What do you get when you divide a quarter by a half?
A half.
Or an eighth by a quarter? Someone says you get a half.
A half.
Good. So a half is the common ratio for this particular sequence. Now, as we did with arithmetic sequences, how do you find the nth term? Suppose I give you the first term and I give you the common ratio, then I ask you for a millionth term of the geometric sequence. Does it mean you have to compute the first 999,000 terms before you compute the millionth term. Well, that's not necessary. There is a formula for finding the nth term. So let's see. I'm going to have a table of values with 2 rows, n, and then an. So at n is 1, my first term is a. Okay. At n is 2, we said you start with the first term and then keep on multiplying by the common ratio. So the next term here should be AR, where R is the common ratio. R is common ratio. A is first term. These are just dummies. I could use anything. I could use P, Q, whatever. But I'm just trying to be consistent because we had used A in the first class, so I stick to A. But they are dummies. You could use any letter that you like. How about 3? Multiply AR by R, loss of indices. So this should be AR squared. Can someone guess what will happen at n? What will be, instead of n, let me put k to avoid confusing with this. What will happen at k? What will be the kth term when n is k? Following this pattern, what will be the kth term?
Is it AR raised to the power k minus 1?
Yes, it should be AR raised to k minus 1. And you can observe from this, A can be written as AR raised to 1 minus 1. So 1 minus 1 is 0, R to the 0 is 1, so 1 times A is just A. You could write AR as A raised to 2 minus 1. You could write AR squared as A raised to 3 minus 1. And take note that this 1 is the position, 2 is the position, 3 is the position. So essentially, if the position is k, then you take A and R is raised to k minus 1. So in general, for a geometric sequence, the nth term an is given by A R raised to n minus 1. Again, just like for arithmetic sequences, geometric sequences are also characterized, and I mean completely characterized by any of its 2 terms. So once I know any 2 terms, whether they are successive or not, does not matter. As long as not 2 terms in the sequence, I can find all the information I need about the sequence. I can find the sum of the number of terms that I'm interested in. I could find the common ratio. I could find the first term. Okay. So let's see. If we try to apply this example here, let's see, find the third term using this formula. Let's try to find the third term in this series. So we know A is a half. R is also a half. The third term, so we said the third term, A3, should be A, which is a half, times R, which is a half. All this raised to n minus 1. So this should be raised to 3 minus 1. So this should give you a half, okay, multiplied by 3 minus 1 is 2. So this should be a half squared. And this gives you an 8, just like we have in this sequence. So in general, this is the nth term of an arithmetic progression. R is the common ratio, A is the first term, n is the number of terms that you are interested in. Is there any question about finding the nth term of a geometric sequence?
Excuse me, sir.
Yes, please.
Can you please show us again how you got R?
R is given in the definition. So I've defined a geometric sequence as a sequence in which the ratio of any 2 successive terms is a constant. And for the sake of my definition, I've chosen that constant to be R. Okay, so if I have the first term as A, to get the second term, well, I know that the ratio of the second term and the first term is R. So for me to get the second term, given the first term, I just multiply the first term by R. Suppose you have this. Suppose you have A as your first term. You're told R is the common ratio. How do you find the second term? Well, let the second term be anything. So let A2 be maybe something K. You don't know what it is. But you know that the ratio between the second term and the first term has to be R. So by the definition for geometric sequence, A2 divided by A1 should be R. Now we don't know what A2 is. It's what we are looking for. So K divided by A1. Well, A1 is just A, the first term should give us R. Then at this stage, make K the subject of the formula by multiplying both sides by A, so that K is simply AR. So this is why if I have A as the first term, the second term is just AR. Term is going to be AR multiplied by R, which is AR squared. You go all the way to AR n minus 1, all the way to infinity, or up to the number of terms that you are interested in. Fair enough? Did I answer your question?
So in short, R is the Did you get my question, sir?
I didn't get your question. I just heard you saying R is, then I lost you.
I'm asking if not the conclusion is that the, R is the product of the first and the second terms.
Not really the product, but the quotient.
Okay.
It's the quotient of any two successive terms. So if I have a third term and a second term, R is the third term divided by the second term. If I had 100th term and the 99th term, R is the 100th term divided by the 99th term.
Okay, okay. Can you use an example of numbers, please?
Sorry?
Can you use an example of numbers?
Yeah, sure.
Instead of,
Yeah,
yeah,
I already gave one. The half, a quarter, an eighth.
okay.
But I can still give another one. No harm.
Yeah, the one that's fractions.
One that is not fractions. Okay. So we can have something like 1, and then 2, then 4, then 8, all the way. So here, the first term is 1. Okay? Then let us compute R. So we said R is the ratio of any of the two successive terms. So R should be 2 divided by 1, which should be the same as 4 divided by 2, the same as 8 divided by 4, all the way. So it's obvious that in this case, R is going to be 2, because 2 divided by 1 is just 2, 4 divided by 2 is just 2, 8 divided by 4 is also 2. So this is an example of a geometric sequence.
Okay.
Is that better?
Yes, much better. Thank you.
And you could also have fractions. So you could have maybe 1, then maybe 0.7, 0.49, 0.343, all the way. So in this case, the first term is 1, then the common ratio is 0.7. So 0.7 divided by 1 is 0.7, 0.49 divided by 0.7 is 0.7, 0.34 divided by 0.49 should also be 0.7, I suppose. Now that we know, so we know the formula for finding the nth term. Given the first term and the common ratio, the nth term is simply the product of the n minus 1th term of R with A. We write as AN is AR raised to n minus 1. It is the R that is raised to n minus 1, not everything. Good. So now let's see how to find the number of terms. Okay. Before that, let me give you an example. So you could be asked, for example, given the following geometric sequence, find the 2000th term, and the sequence is something like 1 minus 2 4 all the way. So this is the sequence. Find the 2000th term for this geometric sequence. So just identify what you need. So you need A, of course, A is 1. That's the first term. Okay. R. So R is going to be the ratio of any of the two terms. So I could take -2 divided by 1. I could also take 4 divided by -2. If you confirm, you'll agree with me that either of these will give me -2. So the common ratio is -2. The first term is 1. I can compute the 2000th term very easily. So by just taking A 2000 as AR n minus 1. So then I just substitute these guys. So 1 times -2 raised to 2000 minus 1. So that's going to be -2 raised to 199. This is going to be the 1000th term. Question? Question? So this is what you need to remember. An is A raised to R, A times R raised to n minus 1. That's what you need to remember. So we know the definition of a geometric sequence. We know the formula of finding the nth term, and we have said that a geometric sequence can be characterized by any of its two terms. I could give you the 100th term and the 50th term, and then I ask you maybe what's the first term or what is the 20th term. So your goal is just to compute A and R, which appear in the formula for the nth term. Now I want us to see how to find the sum of terms in a geometric sequence. How do you find the partial sum of terms? So partial sums for a geometric sequence, a sequence in which the ratio of any two terms is constant. So we are looking for Sn given by A. So that's the first term. I'm just adding. So my sequence is AR squared, AR n minus 1, all the way. So I want only n of them. I will add up to the nth term. So plus AR squared plus AR to the n minus 1. So this is the nth term. My sequence has n terms. Remember, we defined a series as simply a sequence formed by the partial sums. So this is the sum of the first n terms. It's a partial sum of the series. Now, if I multiply this by the common ratio, so A is the first term, the common ratio is R. So let me call this equation 1. Multiply 1 by the common ratio R. So what do we have? Equation 2 will be R times Sn. So Sn times R is simply R times Sn, just like A times B is AB, R times Sn. And then A times R, that's going to be AR. AR times R, AR squared. I'm just applying the law of summation of exponents all the way to AR n minus 1. And then AR n minus 1 itself times R should give me AR n. So we have two equations, equation 2 and equation 1, equation 2, and equation 1. Now subtract equation 2 from equation 1. So what do we have on the left-hand side? The left-hand side, we have Sn minus Rsn. So we get Sn minus R times Sn being equal to, so on the left-hand side, this is what we get. What do we get on the right-hand side? Notice that, so we have A. If I take AR minus AR, well, that's 0. AR squared minus AR squared is also 0. All the way to ARN minus 1 minus ARN minus 1, it's also 0. So the only term that remains here is ARN. Everything in between A and ARN will cancel out. So I will have minus AR to the N. So we have this equation. Sn minus Rsn is A minus ARN. So all the terms that are in here are useless for our sake. You can factor out Sn, okay? So we can factor out Sn. The first term it is 1, the second term it is R. And this side we can also factor out A. A is common between A and ARN. Then we have A into 1 minus Rn. Now R, divide this side by 1 minus R. This side divided by 1 minus R. So the other side, 1 minus R and 1 minus R cancel out. So we have Sn is going to be A 1 minus Rn divided by 1 minus R. So in general, this is the sum of terms. In general, this is the sum of n terms in an arithmetic. This is the sum of terms in an arithmetic progression for which A is the first term and n is the number of terms and R is the common ratio. Any question on this? Any question about this formula? Any question about this formula? What will happen at the point R is equal to 1? What happens at R is equal to 1 for this number Sn? Can someone tell me what will happen when R happens to be 1? Remember, R is simply a real number, so 1 is also a real number. What will happen at R is equal to 1? Remember the domain of a function?
You can't divide by 0.
Good. So what happens to this sum at 1? When R is 1, what happens to this number? It becomes undefined because 1 minus 1 is 0. So we should restrict the domain of this function. So this is a function of A and R, and we restrict that R must not be equal to 1. So this formula only works when R is different from 1. Now someone might ask, how do we find the sum of terms in a geometric sequence where the common ratio is 1? Any guess? How will you find the sum of terms in a geometric progression in which the common ratio is 1? Any trial?
Where there is negative, we put a positive plus, that is.
Now I'm asking about when the common ratio is 1. Do you want an example of a sequence where you have the first term is A is the first term, and then R is 1. So when R is 1, what will be the second term here? Is the first term. R is 1. What is the second term?
1. A, sorry. A, because R will be
Second term is A. How about the third term?
Still A.
A. So all the way to the nth term, you're getting A. So what I'm asking is this, Sn, so now A plus all the way to A. What is this sum? How many A's are you adding? Hello? You're adding n times. What is A plus A up to NS?
Many.
Sorry? No, there are only n terms. There are only n. There are only n of them. So what would the sum be?
AN.
Yes, good. This should be NA or AN, whichever. And you notice that this is just, it becomes an arithmetic progression. So we know that the arithmetic progression, the sum of terms is half of n plus 2a multiplied by n minus 1 times d. Here, what is d? What's the common difference here? What's the common difference? Suppose you have, sorry?
0.
Good. So d is 0. We have first term is a, and n is just n. So let us try to use this formula to find the sum of terms in this sequence. So Sn should be a half of n multiplied by 2a plus n minus 1 times 0. What is n minus 1 times 0?
0.
Good. That is 0. So this is going to be n divided by 2 times 2a. What does this?
NA.
Still get NA. So there are always so many ways of getting these things. Yeah. You just need, all you need is to understand what is involved. You don't need to cram all these formulas. All you need is to understand what's going on. So let me give you an example of a problem where you are supposed to compute partial sums of a geometric series. For example, find the sum. Find the sum of the first 20 terms of a geometric progression. Geometric progression whose first term, no, let me make the problem a bit complex, whose 10th term is 7 and 21st term is 50. Find the sum of the first 20 terms of a geometric progression whose 10th term is 7 and 21st term is 50. Remember, these two terms in the sequence completely characterizes the geometric sequence. Once I know any two terms, I can find all the information I need. So the formula is that Sn is a into 1 minus r to the n divided by 1 minus r. Of course, r is not equal to 1. We've seen that when r is equal to 1, the geometric sequence turns out to be an arithmetic sequence. And the formula is just the number of the terms times the first term. It's just one term repeating itself. Now, we have the 10th term. So in general, an is a times r raised to n minus 1. We want to use this formula on these two terms to find a and r, because all we need here is a and r. N is already given us 20. So we have 10th term. So A10. A10, I'm just substituting A times R raised to 10 minus 1, which is A times R raised to 9. A21. A21 is A R raised to 21 minus 1, which is A R raised to 20. This is given as 7. This is given as 50. Again, we get back to our familiar friends. Simultaneous equations, but in this case, they are not linear because you can see it is nonlinear in R. The exponent of R is bigger than 1, so it's no longer linear, but it's still a simultaneous equation. The first equation is that 7 is AR raised to 9. The second equation is that 50 is AR raised to 20. How do you solve such kind of a problem? Any ideas from the class?
You subtract.
Sorry?
You subtract the two equations.
Subtracting the equations, will that help? You think that will help? Because if I subtract this side, I'll get a number, but this side, I will still have something nonlinear. So for example, 7 minus 50, well, that's minus 43. When I do this subtraction, I'm getting A into R power 9 minus R power 20. Still I've not eliminated anything. I still have A and I still have R to some power. So subtraction would not be a good idea. Thank you. And now you're thinking of elimination. Any other idea?
Yeah, we can actually find A in each equation and then equals them, like equal the first A and the second A. I don't know if I'm making sense.
So from the first equation, you can write this in terms of A. So this
Yes.
means A is simply 7 divided by R raised to 9. This other one means A is simply 50 divided by R to the 20. Let's see. So it is still the same A. So we can equate this guy. So 7 divided by R power 9 is the same as 50 divided by R power 20. Now from here we can find R. Okay. So I could cross multiply. So I have 7 R 20 minus 50 R power 9 is equal to 0. So I've done 7 times R to the 20. Yes, and then R to the 9 is 50. Then I brought them on one side, so I equate this to 0. Now at this stage, you can factorize. What's the common term here? What's the common term here in this expression?
Or
the common term is R power 9. So this R power 9 is the common term. So factor out, you have R power 9 into, so R power 9 goes in the first term as 7R power 11. I'm using the laws of addition of exponents. So R power 20 divided by R power 9 is simply R power 20 minus 9. 20 minus 9 is 11. This side, I have minus 50. All of this is equal to 0. Then you remember the property of real numbers, precisely an integral domain. We said that the product of any two real numbers is 0 if and only if one of these numbers is 0. So in this case, this product can only be 0 if R power 9 is 0 or 7 R power 11 minus 50 is 0. So if R power 9 is 0, 0 times anything is 0. If 7 R power 11 minus 50 is 0, 0 times anything is 0. Now the first one, when r power 9 is 0, well, that simply means r is 0. Well, that's not very interesting. It's a trivial sequence. So this is a sequence where we'll have an a and all the other terms will be 0. That's not a very interesting sequence. So let's consider this second one. Now here, this is the same as 7r power 11 is equal to 50. You can make r power 11 the subject. So r power 11 is 50 divided by 7. Now you have r power n is 50 divided by 7. We gave a general solution for nth power. So this is called a power equation. R raised to some integer power. To compute r, simply find the nth root, in this case the 11th root. So r is going to be 50 divided by 7, all raised to power 1 over 11, or the 11th root of 50 divided by 7. Okay, this is going to be your r. Now that we have r, we can use this in any of these equations to compute a. So using this value of r, we can put it anywhere and find a. Once you have a and r, the formula was Sn is a into 1 minus r to the n divided by 1 minus r. So the r that you found here and the a that you will find, you plug in this formula and find the sum of terms. Remembering that n is 20. Is there any question? So usually you'll be given nice sequences. This is not a very nice sequence because we're ending up with 11th. So this is going to be actually going to be some irrational number. 11th root of this fraction. This is not a very nice sequence. In the case of an exam, I will not give such sequences.
I have a question.
Yes, go ahead.
So what about the value of a?
You will use this value of r in any of these two equations. So the value of a is very easy to find. Let me say I take the first one. So somewhere we had that a was r power, what did I write up here? A was it 4 or 5 or 7 divided by r power 9, something like that. Now this should be 7 divided by r. R is this guy. So r is going to be the 11th root of 50 divided by 7. So Abdi Hakim, this will be your a. A is going to be the 7 divided by the 11th root of 50 divided by 7. And this should be raised to 9. Raised to 9, because it's r raised to 9. Okay?
Yes, sir. Thank you.
You just compute this in the calculator. You know, find the nth root using a calculator. You guys know how to find the nth root using a calculator? You know the power button? Finding the nth root is like
equals 2.62.
It's like, yeah, so you also find r, then put in this formula. N is 20. Any question on finding partial sums in a geometric series? Finding partial sums in a geometric series. Question? Okay. Now, before we ditch geometric series, there's another type of geometric series which I would like to bring to your attention. It's called infinite geometric series. Infinite geometric series. And we would like to study those ones which converge, those ones whose sums are finite. There are some series whose sums will not be finite. Some series whose sums will be infinity or undefined. But here I would like to study a series whose sums are finite. Just to give you maybe some motivation. Suppose you are eating a cake, which is circular in shape. And how you're eating this cake is that you start by eating half of the cake. So this is at stage 1. At stage 2, you only have the unshaded part remaining. So at stage 1, I ate the shaded part. So I'm only remaining with the uneaten part at stage 2. At stage 2, again, I eat half. So what remains is this guy. This is at stage 3. Again, at stage 4, I eat half of this. So at stage 4, I eat half of that. So that will be something like that. And this is what I'm remaining with. And this process goes on and on. This process seems unending. You can go on and remember as the stages increase, the quantity you are eating also decreases. So you'll end up with an infinite sequence of activities. Now the question we're asking is, can we have a series where infinitely many terms can add up to a finite number? But I give you a series where the number of terms is infinite. Is it possible to find those series whose sum of infinite terms is a finite number? Say 5. Can 5 be written as sum of infinitely many terms? So in this case, let's say now we change the problem. We change the problem now. We want to find the quantities that you have been eating. So you started with 1 cake. Now let us add the quantities that you're eating at each stage. So at stage 1, you're eating half of the cake. We want to add the quantities that you will have consumed. At stage 1, we ate a half. At stage 2, we ate a half of the half that remained. What is a half of a half?
A quarter.
A quarter. So at stage 2, you ate a quarter. At stage 3, again, you get a half of what remained. So a half of a quarter.
An eighth.
An eighth. Of course, in general, you're eating a half raised to n, and it goes on and on forever. So remember, we started with 1 cake. This sequence has infinitely many terms because we'll keep on dividing until you get to the subatomic particles, very tiny particles, which you cannot see with your bare eyes. You might have to use some very high resolution microscopes because you won't be able to see the sizes. This process will continue infinitely. So in other words, there are infinitely many terms in this sequence. But remember, we started with just 1 cake. So it means, however way, in whichever way you add this number of terms, it will never be more than 1 because you have only 1 cake. So the paradox is you have infinitely many terms, but we are sure the sum cannot be more than 1 because we started by just 1 cake. So we cannot add this and find more than 1 cake. So what we are ending up with is that a half plus a quarter plus an eighth plus 1 over 2n plus all the way to infinity. This cannot be more than 1 because we started with just 1 cake. Somehow it has to be 1, actually it has to be 1. So this means 1 can be written. So 1 is a finite number, 1 is less than infinity. Remember the number line has this behavior, so this is 0, this is 1, this goes to infinity. That this 1 can be written as a sum of infinitely many terms. Let us try to use the formula that we had before for geometric sequences. So in this case, our sequence is determined by, so let us first of all find a formula for this sequence. Of course, we know A is a half, that is the first term. What's the common ratio? What's the common ratio here?
1/2.
Sorry?
1/2.
The ratio is a half. So how do you find the sum of n terms? So the sum of n terms should be A 1 minus r to the n, all of this divided by 1 minus r. Okay? So this should be a half, that is A, then 1 minus a half raised to n. All of this divided by 1 minus a half. Let's see what this gives. So in the numerator, you have outside you have a half, inside we have 1 divided by a half raised to n. Then in the denominator, 1 minus half is simply a half. This half cancels this half, so you end up with Sn being 1 minus a half raised to n. Let us see for some few values of n what this sum will be. Let's say we put n is 1,000,000. So use your calculator to compute as 1,000,000. I want you guys to compute 1 minus a half raised to 1,000,000. Tell me what you get. Someone also to compute s power maybe 20 billion. Use a calculator. So that should be 1 minus a half raised to 20 billion. It's an observation I'd like us to make before we conclude.
The first one is 1.
Are you sure?
Yes, I got the same thing.
Got the same thing. Okay. How about the second one? The calculator is still thinking. Is it too big for your calculator? Remember, you can also do this in Python. This
Still 1.
Still 1. Remember, I said that, how did we form this sequence? We were eating a cake. And I said that, I mean, logically, you just had one cake. So there is no way in which infinitely many activities of eating this cake will end up producing more than one cake. So I was not expecting the sum to be more than 1. And you see at 20 million, you're getting 1. Well, this is not true. In general, I asked you because I know it's not true. The problem is your calculator, the accuracy of your calculator. Your calculator is only accurate up to maybe 10 decimal places. That is just to truncate. So this should actually be 0 point something. Very many decimals after 0.9 and then very many decimal places. So what I wanted to conclude here is that in general, so here we have r being a half. A half is a number which is less than 1. In general, Rn goes to 0 as n goes to infinity, as long as the absolute value of r is strictly less than 1. So if you pick a half, try computing a half raised to any big number, you'll get 0. Actually, any fraction, if you pick maybe a quarter raised to any big number, it will always get to 0. So what happens is this: if you have an infinite geometric sequence where the common ratio is strictly less than 1, so in general, we had Sn as A into 1 minus r to the n, all of this divided by 1 minus r. But the observation is that as n goes bigger and bigger, this term Rn goes to 0. So let's say you're adding infinitely many terms. I will denote that by S infinity. This should be A times 1 minus 0, because as n grows bigger, this term Rn goes to 0. Divided by 1 minus R. So this should be equal to A divided by 1 minus R. So the take home today is that for an infinite geometric series in which the common ratio is strictly less than 1, the sum of terms is given by A, the first term, divided by 1 minus R. For example, the sequence that we had, of course, up to 20 billion was giving you 1. But if I wanted you to find S of a million terms, you just take the first term was a half divided by 1 minus a half, which is the common ratio. Because a half was the common ratio. Noting that a half is less than 1. So this is going to be a half divided by, what is 1 minus a half? What's 1 minus a half?
A half.
1/2.
A half. So a half divided by a half?
1.
Half divided by half is 1. So this is the formula for the sum of terms in an infinite geometric series in which the common ratio is less than 1. If the common ratio is 1 or bigger than 1, this sum will not be finite because the number of terms will be growing at each and every subsequent terms as you go in the sequence. Any question up to there? Before I give another example different from this. Question? Okay, let me give an application of this and something that you've seen before. But we need to add infinitely many terms for us to be able to solve a very easy problem. Using infinite geometric series. Infinite geometric series. Write maybe 2.45 6 recurring at 156 as a fraction. Have you seen recurring decimals before in your life? Recurring decimals?
Yes.
2.456 is simply 2.4, then 56 is recurring to 56, 56, 56, on and on. Infinity. We want to write this as a fraction, but using infinite geometric sequences. How do you go about this? So we need to form a geometric sequence out of this and then use the formula to write this sum as a fraction. And we'll confirm this with the calculator to see if what we get is actually a representation of this number. So remember, you could write this as 2.4 plus 0.0565656, like that. I've just decided to break this at the point where it's recurring. So I have 2.4, then plus 0.056565656 recurring. 2.4 as a fraction is simply 24 divided by 10. Okay? How about this number as a fraction? Well, I could write this number as 0.056 plus 0.000, how many zeros? 3 zeros, and 56, on and on. So we have 24 divided by 10 plus What is this as a fraction? 0.056
56 over
1,000.
1,000.
or 1,000 plus, how about the second one here?
56 over 10,000. 100,000.
Over 100,000. Again, you'll get a 56 over something. You don't know, but we're not interested in. Notice that from this point onwards, you have an infinite geometric series. Here you have infinite geometric series. So it is this which I need to write as a fraction using the formula for finding sums of a geometric series. So what we have, the first term here is 56 out of 1,000. This 24 out of 10 is not in the series. It's only this second part which is in the series. So the first term is 56 divided by 1,000. I need to find the common ratio. What's the common ratio? Well, just these two terms is enough for me. I just compute 56 divided by 100,000. All this I'm dividing by 56 divided by 1,000. And this should be 56 divided by 100,000 times 1,000 divided by 56. So what do we get? 1,000 divided by 100,000 is 1 divided by 100. So here, I know here we will have 1 million. When you add, yes, so here you have 1 million. There. So we have R, it's actually less than 1. 1 over 100 is less than 1. We have an A. We can find the sum of the infinite terms in this sequence because it's recurring means this pattern goes on up to infinity. So using the formula, the sum of terms, infinitely many terms, is A divided by 1 minus R. What is A? 56 divided by 1,000. All this divided by 1 minus R. So divide this by 1 minus 1 over 100. Well, that gives you 56 divided by 1,000 times. So remember, I can change division to multiplication by simply inverting what we have here. But what is 1 minus 1 divided by 100? That should be 99 divided by 100. So when I invert, I get 100 divided by 99. You check if this is true. And so then we just do the calculation. So we get 56 divided by 990. So this second part is simply 56 divided by 999. So let's see. Our number 2.456 recurring should be 24 divided by 10 plus 56 divided by 990. Can someone work this as a fraction and give us? Of course, the LCM is 990. So 10 into 990 is 99. What is 99 times 24? 99 times 24?
2376.
76. Then it goes there 1, so this is 56. So we should have, what is this sum? 2376 plus 56.
$24.32.
2432 divided by 909. Try to press this in the calculator and see what it gives. 2432 divided by 909. If we did not make any mistake, we get 2.456 going on and on. That is if we did not make any mistake. What are you guys getting?
Yes, the same thing.
Them.
Good. Questions? So all I needed was this formula, and I also needed to extract the part of the number where the infinite geometric series appears, so that I take out the term 24/10, which is not in the infinite geometric series. Then I convert the part which is in the series as a fraction, which is the sum of infinitely many of those guys, and then I add it to 24 divided by 10. Is there any question up to there? No one is asking questions today. Are these things too hard?
Excuse me, sir, when you calculated that after you got 2432 over 990, do you have to leave it at that, or can you leave it as a mixed fraction?
There's no problem. You can leave it as you wish. There's no problem.
Okay.
Okay, in case there are no questions, then let us look at our last concept of the day, which is binomial expansion. Binomial expansion. Binomial expansion. Binomial expansion. So we will mention the last theorem of this topic. Look at a couple of theorems. For this course, the last theorem which I would like you guys to understand is the famous binomial theorem. But first of all, what's a binomial? Definition. Let A and B be real numbers. Well, it doesn't matter. They could be complex numbers, they could be quaternions, they could be octonions, whatever, but we're just trying to restrict ourselves to the real line. But the binomial theorem works for any number system. An expression of the form A plus B is called a binomial. Binomial. So bi means two. So expression of this form is called a binomial. And in this topic, we are interested in expanding this binomial. We want to find the powers. So the goal is to find integer powers. Integer powers of A plus B. That's our goal. Let me create a table of values here, and then we want to see what does A plus B raised to n look like. Integer power. So maybe I should put non-negative to find non-negative integer powers. Of course, the theorem holds for even negative integer powers. It also holds for rational numbers. You can apply it for fractions, but I want us to restrict ourselves to non-negative integer powers. Because once you understand this, you can generalize this to any number system that you're interested in. So let's start with 0. 0 is a non-negative number. What is A plus B raised to 0? What's A plus B raised to 0?
1.
Sorry?
1. 1.
A plus B raised to 0 is 1. How about when n is 1, get A plus B raised to 1. What is A plus B raised to 1? What is A plus B raised to 1?
A plus B.
Plus B.
A plus B.
That's just A plus B. Now let us start the journey. a plus b squared. What is a plus b raised to 2? Well, so by definition, a plus b raised to 2 is simply a plus b times a plus b. Remember, the definition of something squared is something multiplied by itself. You know, x squared is x times x. So I'm just taking a plus b multiplied with a plus b. We've done expansion, okay? So we just take all the terms in the first bracket multiplied by all the terms in the second bracket and then add them up. So we will take a multiplied by a plus b multiplied by a plus b. A times a, I'm now opening brackets. A times a is a squared. A times b is ab. Well, b times a is ba. B times b is b squared. We all know that multiplication of real numbers is commutative. So I've defined a and b to be real numbers. So ab is the same as ba. Just like 4 times 5 is the same as 5 times 4. It doesn't matter which one you start with. So this is simply going to be a squared plus 2ab plus b squared. So here we have a squared plus 2ab plus b squared. We will stop at 3 and then we generalize. A plus b cubed. So we already have a plus b squared. I want us to use that to find a plus b cubed. So again, by laws of indices, a plus b cubed will be the same as a plus b multiplied by a plus b squared. Just like x cubed is x multiplied by x squared. And you notice that when you use the laws of exponents, so adding the exponents, this is a plus b raised to 1, simply itself. 1 plus 2 gives you a 3. We already have this expression. So just put a plus b multiplied by a plus b squared is this guy. This is a squared plus 2ab plus b squared. Well, it's already looking messy, but we'll stop at this point. I'm not going to continue further. I'll just generalize from this. So this is simply, I'm opening the brackets. I want to multiply all the terms in the first bracket by all the terms in the second bracket. Then I add them up. So a multiplied by a squared plus 2ab plus b squared plus b multiplied by a squared plus 2ab plus b squared. Okay. Don't be scared. I know most of you have already lost interest in this, but it's going to be nice. I'll give you a very nice theory about this. You don't have to do this. So a times a squared is simply a cubed. A times 2ab is 2a squared b. A times b squared is ab squared. B times a squared plus b times 2ab is 2ab squared. B times b squared is b cubed. So here identify the common terms. A squared b, and we have a squared b. So here we will have a cubed plus 2a squared b plus a squared b. That's going to be 3a squared b plus, this is a b, ab squared, and then this is 2ab squared. So 2 plus that is going to be 3ab squared. And then lastly, plus b cubed. Okay. There are some few observations I would like us to make before we generalize this. Notice that when n is 0, there's just one term. When n is 1, you have 2 terms. When n is 2, you get 3 terms. 3 terms. So 3, this is that 1 plus 2 plus 1, 2, 3. When n is 4, we are getting 4 terms. 1, 2, 3, 4. So we can actually guess that a plus b to the n will have n plus 1 terms, because at 0, we're getting 1, 0 plus 1. At 1, we're getting 2 terms, 1, 2, which is 1 plus 1. At 2, we're getting 3 terms, 1, 2, 3. 3 is 2 plus 1. At 3, we're getting 4 terms, 1, 2, 3, 4. 4 is 3 plus 1. So in general, when you have a plus b to the n, you're expecting n plus 1 terms. The other observation we need to make is about the exponents. Notice that when you have a plus b raised to 1, the highest exponent is 1. When you have raised to 2, the highest exponent is 2. When you have raised to 3, highest exponent is 3. So the other observation is that highest exponent is n, because at 0 is 0. At 1, the highest exponent is 1. At 2, the highest exponent is 2. At 3, the highest exponent is 3. So at n, we expect the highest exponent to be n. And then there's another pattern. Lastly, the last observation I will make is that exponents of a decrease from n by 1 to 0 as exponents of b increase by 1 from 0 to n. So here you have at 1, you have a power 1, b power 1. At 2, you have a squared. That is what you start with. Then the next term, there is an a power 1. In the last term, there is an a power 0. So the powers are decreasing by 1 for the first term. The second term, which is a b, first you have a b power 0, which is 1. There's a silent 1 here. Then you have a b power 1, so 0 plus 1. Then a b power 2, 1 plus 1. Same for the case of 3, a power 3, a power 2, a power 1, a power 0. And then b power 0, b power 1, b power 2, b power 3. Again, at each and every stage, every term, the sum of the exponents should be n. So here, there's an a power 1 and a b power 0 for this first term. 0 plus 1 is 1, and 1 is the power. If you go to the case of 2, in the first term, there's an a power 2 and a b power 0. 2 plus 0 is 2. In the second term here, there's an a power 1 and b power 1. 1 plus 1 gives you 2. In the last term, there's a b squared and a power 0. 0 plus 2 gives you 2. Lastly, for the case of 3, you have an a power 3 and a b power 0. 3 plus 0 is 3. This term, you have an a squared and a b power 1. 2 plus 1 is 3. The third term, you have an a power 1 and a b power 2. 2 plus 1 is 3. Lastly, you have a b power 3 and a power 0. 3 plus 0 gives you 3. So at every stage, the sum of the exponents is the power to which you are raising the binomial. And you also notice that there is a pattern in the exponents. So the first exponent starts from n, and as you go successively, the powers keep decreasing from n minus 1 up to 0. The powers of the second term, which is b, increase from 0 to 1 to 2 all the way to n. In general, this pattern will always repeat itself. So whether you continue this table to 4, 5, 6, 7, you'll keep getting the same pattern. So our worry should be, we already know these terms. We already know in general. We know how these powers behave. So our worry now is how about these coefficients? There's a 2, there's a 1, there's a 1, there's a 1, there's a 3, there's a 3, there's a 1. Can we come up with a way of finding these coefficients? Because that is all we need to know now. We already know that there will be n plus 1 terms. The first term will be a to the n, and the powers will keep decreasing as you go along, and the powers of b will increase as you go along. Increase the powers of b by 1, increase the powers of a by 1. And at each and every term, the sum of the exponent is n. So our headache now should be, how do we find a generalization for these coefficients? So let me show you some pattern that you can observe. From this our table, I just want to write the coefficients alone. I want to ignore these terms because we already know the behavior. So at n is 0, well, there is only 1. At n is 1, coefficient of a is 1, coefficient of b is 1. So we have a 1 and a 1. At n is 2, coefficient of a squared is 1. Coefficient of 2ab, well, that's 2. Coefficient of b squared is 1. Lastly, for our case, at 3, coefficient of a cubed is 1. Coefficient of 3a squared b, well, that is 3. Coefficient of 3ab squared is also 3. And lastly, coefficient of b cubed is 1. This is the famous Pascal triangle. It's called Pascal's triangle. Pascal's triangle. And notice that, so I start with 1, 1 and 1. Then now to get these 2, I simply add 1 plus 1 to get 2. At this stage, I start with 1, then I add 1 plus 2 to give me 3. And then here I have 2 plus 1 to give me 3 and a 1. So let's see, at 4, I'll start with 1. The next term will be 1 plus 3, 4. The next term will be 3 plus 3, which is 6. The next term will be 3 plus 1, which is 3. The last term will be 1. So 3 plus 1 is 4, sorry. And you notice that as expected, there will be 5 terms because the coefficients are 1, 2, 3, 4, 5. But now, suppose someone asked you to expand maybe to the power of 20. We don't want to be doing this for 20 rows. It will be so hectic. We'll waste a lot of time doing this. So we will generalize how to find binomial coefficients. In the next class, we'll see how to find binomial coefficients. Then once we have found the binomial coefficients, we already know the pattern in the terms, we'll be able to do our binomial expansion. So what remains here will take about 20 minutes in the next class, and then we are done for college algebra. Any question? Questions? Any questions?